For the finite summation that is provided here, we want to solve it using two methods, one quick direct proof method and the other one a mathematical induction method. If we take a look at this summation, it has a general term of n divided by 2 to the n. So it's basically 1 over 2 plus 2 divided by 2 to the 2 and then plus 3 divided by 2 to the 3 and so on and so forth. Does it converge? What is the value? Okay, so direct method. Let's name this whole thing as S, and I can write it in a more compact fashion using sum notation, sigma k from 1 to n and then k divided by 2 to the k. Obviously I can write it as this way as well, sigma, so 2 times sigma k from 1 to n k divided by 2 to the k plus 1. So it's effectively as if I multiply divide by factor of 2 the whole thing, which doesn't change anything. Now I can rewrite this summation therefore in this format, 2 times, so 2 times sigma k from 1 to n and then k over x to the power k plus 1 where x is 2. It's the same thing, and of course this can be again rewritten as sigma k from 1 to n k times x minus k minus 1 when x is equal to 2. If you take a look at what is here, that very much looks like the derivative of with respect to x of x to the negative k and then minus sign. If you compute this very simple first, let's say first order derivative, you would see that the derivation of x to the negative k will give you this. Alright, so therefore I'm going to write my summation in the form of 2 times sigma k from 1 to n, and there is a negative sign that I'm going to put it right behind everything, so my summation is negative 2 times sigma from k 1 to n, and then I have the derivative with respect to x, x minus k. Of course, after doing that, x equal to 2. I can push the summation into the derivative because the index of summation doesn't have anything to do with x, so minus 2 derivative with respect to x sigma from k 1 to n and then x minus k after this whole computation done and after taking the derivative, then setting x equal to 2. Okay, so let's deal with the thing that we have inside the parentheses here, this summation. If you take a look at this summation, it purely looks like, given index k from 1 to n, it just looks like 1 over x plus 1 over x squared plus 1 over x cubed plus ellipsis and up to 1 over x to the power n. So the negative power is showing itself, manifesting itself in the form of 1 over x and plus 1 over x squared and so on and so forth. This is, of course, a geometric series. So we have a geometric series summation in which we have the first term 1 over x. So this is our first term of summation, and you can see that the common ratio that multiply each term to get to the next term, r, or common ratio, is simply 1 over x. So that is the common ratio of the geometric sum or series. So common ratio. And then we have the final term. So first term is t1, term 1. And then we have the final term 1 over xn. So this is the final term of the series. It's a finite series. It is easily it can be easily shown that this result of this summation is simply in the form of t1 minus rt, let's say n, or the final term, divided by 1 minus r. So in this case we are dealing with 1 over x minus r is 1 over x, and then the final term is 1 over x to the n divided by 1 minus 1 over x. Okay, so if I multiply both the numerator and denominator by x, I get 1 minus x to the power negative n I just rewrote this as x to the negative n divide by x minus 1. So this is the compact form of what this summation is. Okay, the good thing is now the next step is taking a derivative out of this guy. As you can see here, I have to take a derivative so to compute the sum. That is my ultimate goal. So I am going to write here, let me change the color. Okay, so I am going to write here, and to open up some space here is okay. So I can write, therefore I can write my sum is equal to, so the target sum is equal to -2 as is here, and then we have derivative with respect to x, so derivative with respect to x, and then this thing, which is 1 minus x to the negative n divided by x minus 1, and of course after I compute everything I have to substitute x equal to 2, so it becomes -2. Alright, this derivative is a simple one, so it's derivative of numerator, which is plus n x negative n minus 1 times denominator x minus 1, so x minus 1, and then minus derivative of denominator with respect to x is 1, and then minus -1 plus x minus n divided by denominator squared, which is x minus 1 squared. And then I don't need to directly compute this, because I need at the end of the process I'm supposed to substitute x with 2. So let's do it now, because that helps a lot. If we substitute x equal to 2 in denominator, then denominator effectively becomes 1, because it's 2 minus 1 squared. So I'm gonna quickly just write -2 times, so keep n, substitute x with 2, so n 2, and then I can write 2 to the minus n minus 1 as 1 over 2 to the n plus 1. And of course this component becomes 2 minus 1, which is 1, so I'm not going to even write it. Keep the -1, so -1, and then this one becomes 2 to the negative n, which is plus 1 over 2 to the n, which I can write it as 2 divided by 2 to the n plus 1. Okay, so the last step is just simplification, and by that let's keep it as 1 over 2 to the n for now. Okay, so by the last step is simplification. -2 multiplied by this whole thing will give us 2. That is the result of -2 times -1, and minus, I get n plus 2 divided by 2 to the n. That's it. This is the answer for the summation that we were looking for. So we proved that using the first method, which is a direct method, we proved that this summation, this finite summation, converges, and actually converges to this value. If we are interested to make it an infinite summation in the form of, so let's say limit, so if we take a limit of this summation when n goes to infinity, so basically we are computing 1 over 2 plus 2 over 2 to the power 2 plus 3 over 2 to the power 3 plus ... plus n over 2 to the power n, and then this goes to infinity, then it becomes limit of 2 minus n plus 2 divided by 2 to the n when n goes to infinity, which obviously this component here goes to 0, this component here goes to 0, and the answer becomes as simple as just 2. So this whole infinite summation when n goes to infinity converges to 2, as well. Okay, so this is using the first method, which is the direct proof. The second method is mathematical induction. So let's check the mathematical induction here. So math induction. What are we proving? Now we are trying to prove that. Prove sigma from k1 to n 2 to the k, k divided by 2 to the k is equal to 2 minus n plus 2 divided by 2 to the n. Or if we wanted to write it as was the case before, it is exactly this portion, which is the left hand side of summation, that is now presented this way. So if you want to expand it, just for the sake of visualization, it would be 1, as was the case, over 2, 1 over 2, plus 2 divided by 2 to the 2, plus 3 divided by 2 to the 3, plus, and then n divided by 2 to the n is equal to 2 minus n plus 2 divided by 2 to the n. So that is what we want to prove using math induction. Alright, so in math induction we have to go with basis step. So basis step, and in basis step we have to check for the basis point. Obviously the basis point is k equal to 1 or n equal to 1. So basically it's as if we are saying for basis point, so this is our let's say statement p of n, which indicates that left hand side is equal to the right hand side. Let me highlight that so this is the left hand side and this is the right hand side, and we are stating this equivalence as p of n. So we are saying left hand side for a given n as integer. So for all, let me put it this way so that it's official, for all n p of n where n is an integer, is a positive integer. So for a given positive integer n, smallest value 1, we want to say that for all n p of n, which p of n is this statement, left hand side equal to right hand side. So basis step is n equal to 1, prove p of 1 is true. So p of 1 says left hand side simply is 1 over 2, obviously. So left hand side is 1 over 2 and the right hand side is 2 minus instead of n I'm gonna substitute 1. So 1 plus 2 divided by 2 to the 1. So it becomes 2 minus 3 over 2, the right hand side, which is obviously 1 over 2. And you can see that right hand side and left hand side match. They match. So as a result, basis step is true, is correct. So p of n is correct. We prove the basis step. Now next step is going after inductive step, so or induction step. In inductive step, what we are saying is make the assumption, so this is basis step, this is inductive step. In inductive step, what we are saying is let's make the assumption that, so assume that p of k, which is true, which is, so this is inductive hypothesis, which is the statement that 1 over 2 plus 2 over 2 plus 3 over 2 to the 3 plus ... up to k over 2 to the k, the left hand side is equal to 2 minus k plus 2 divided by 2 to the k. So again, right hand side of inductive hypotheses and left hand side of inductive hypotheses. This is referred to as, this whole thing is referred to as inductive hypotheses. assumptions, the assumption that we have. Okay, so we make the assumption this is correct. Then the target is, then with that assumption, prove P of k plus 1 is true. So we need to prove it. Basically what we are saying in mathematical induction, for all k, where in this example k is a positive integer, we are saying if P of k is true, then we need to prove that P of k plus 1 is also true. So we start from, it's like a direct proof. We start from a hypothesis that is assumed to be correct, and we need to arrive at a conclusion. So how can we do this? Alright, we start by just saying, okay, let's write P of k plus 1. What is it? The P of k plus 1 is very similar to what is written here for P of k, except it has one extra component here, and then we have to substitute n with k plus 1. So let's write it. P of k plus 1, so I'm going to write it here. It will start with 1 over 2, 2 over 2, and dot dot dot, but it goes up to k over 2 to the k, and then k plus 1 over 2 to the k plus 1. And on the left side, maybe if I shift it, then it's going to help us, because I don't have enough space here. So I'm going to shift the whole thing a little bit this way, so that there is some space. Okay, great, I have enough space now. So I can write for the left hand side, for the right hand side, I can write, substituting here n equal to k plus 1, because I'm dealing with P of k plus 1. So it becomes 2 minus k plus 1 plus 2, which is k plus 3, divided by 2 to the k plus 1. So this is my left hand side that I need to get to. This is the this is the left hand side of the target, and this is the right hand side of target. The busier one, the more complicated one, is the obviously left hand side. So let's start from there. I would say left hand side of P of k plus 1. The nice thing about this left hand side is the very easy to see connection or relation of that to left hand side of hypothesis. You can see that this portion of left hand side of P of k plus 1 is exactly copy paste of left hand side of P of k. So using inductive hypothesis, or the assumption given to us, we can substitute that with right hand side of hypothesis. So I am going to write using, so here is using inductive hypothesis, or the assumption that is given to us. I am replacing, or basically I am just substituting the portion that I showed you in red with this. So therefore I can rewrite 2 minus k plus 2 divided by 2 to the k. That's the substitution for the portion highlighted in red, and keep the rest in the left hand side. K plus 1 divided by 2 to the k plus 1. Okay, so let's just do a simplification here. It's very straightforward. I can multiply numerator and denominator for this ratio that I have here by a factor of 2. So it becomes 2 minus 2k plus 4, and it becomes 2 to the k plus 1, which has the same common denominator as the other one. So I can share the denominator, 2 to the k plus 1. And I can put this one as it is. So plus, there is a negative sign here that we need to be careful. So maybe I write it this way so that there is no confusion. 2 plus, and then plus k plus 1. So as a result, I'm going to get 2 plus and it become negative 2k plus k negative k, and the negative 4 plus 1, which become negative 3, divide by 2 to the k plus 1, which obviously we can write it 2 minus k plus 3 divide by 2 to the k plus 1, and that is exactly what we needed to get to, because if we go back to the target right hand side of the p of k plus 1, you can see that there exactly we got to it, because k plus 1 plus 2 is exactly k plus 3, and just to avoid confusion, this negative sign is applied to the whole thing. So this negative sign is applied to the whole thing. Alright, so we quickly used basically the inductive hypotheses, that the assumption we had, to substitute for a portion of the left hand side using the information we had, and we arrived at the right hand side of the target. So with this we are done using mathematical induction. So basically this also concludes the inductive step. That is true. From p of k we can really, so we prove this, from p of k we can really get to p of k plus 1. So therefore, since basis step and inductive steps are both true, then by mathematical induction we can say for all n, p of n is true where n is a positive integer. Okay, so in summary, we tried and we examined two proof methods. One is proof by mathematical induction, which is presented here as the second method, and the other one is proof by just direct proof method using some tricks involving taking derivative and then using functions and derivation to just find out that actually this summation converges to a finite value that has a closed form representation, and then we can also take a limit of that when n goes to infinity to find that actually even if this summation is going to be a infinite summation, then it will still converge to value 2. I hope that this example is helpful to show in terms of showing how we can use both direct proof methods and also the mathematical induction to find the solution of a mathematical summation. Thanks for watching.